characteristic equation and eigen decomposition. Today we'll be dealing with spectral theorem. So spectral theorem is applicable for a real symmetric matrix. So if you are given a particular matrix, first you will have to check whether it's a real matrix. Real matrix means the entries of that particular matrix should be from real numbers, and it should be symmetric, which means A transpose should be equal to A. If these two conditions are satisfied, then the spectral theorem can be applied to that particular matrix. And the theorem states that all eigenvalues of A are real, and also it states that there exists an orthogonal matrix P such that P transpose AP equal to D, where D is a diagonal matrix. In the later case, in the before case where we discussed about the eigen decomposition, we had P inverse AP equal to D if A was diagonalizable. Now in this particular case, if A is real symmetric matrix, then in that particular case we need not find P inverse, we can just directly take P transpose. Okay, that's the difference where we apply spectral theorem. So let's do some problem on spectral theorem. First question is, using spectral theorem, orthogonally diagonalize the given matrix. So first what we do is, to apply the spectral theorem, we check whether A is real. All the entries 4, 1, 1, 4 are all real numbers, so it's a real matrix. And now what we do is, we'll just try to find A transpose. A transpose, when you are seeing A transpose, it's 4, 1, 1, 4. It's same as A, which means A is real and symmetric, so it is orthogonally diagonalizable. Okay, that's what the theorem is. It is orthogonally diagonalizable. So let's try to find P. So for P, we'll find the eigenvalues, then the eigenvectors, and we'll construct P. So for that, we have the eigenvalues. To find the eigenvalues, we find determinant of A minus lambda I. We have A minus lambda I. Then we'll take the determinant, and we'll factorize them, and we'll find lambda minus 5 into lambda minus 3, which implies that eigenvalues are lambda 1 equal to 5 and lambda 2 is equal to 3. These are the eigenvalues. Now we'll find the corresponding eigenvectors. How do we find? We'll find the matrix A minus lambda I. The matrix will be, just let us look into that. So when lambda equal to 5, A minus 5i into x equal to 0, we'll find this x. So A minus 5i is given by this particular matrix, minus 1, 1, 1, minus 1, and instead of x, x will be a component of R2. So let's take x to be equal to xy. Okay, this x is the vector x, and the vector is given by x and y. Okay, the column matrix xy. So now when multiplying both this matrix, this is a 2 by 2 matrix and this is a 2 by 1 matrix. When multiplying them, we get minus x plus y is equal to 0. Okay, so we have minus x plus y is equal to 0. This implies x equal to y. And if x is equal to y, we had our vector x was equal to xy. Let us take it to be v. Okay, then it will be fine. Let us take it to be v1. So instead of v1, for v1 we have, let v1 is equal to v1 is equal to, it was equal to xy, and here we have x is equal to y, so that will be y, and let us take y to be arbitrary, let it be 1, 1. So our eigenvector is 1, 1. Okay, and now similarly we'll take lambda equal to 3, and we have a minus 3i into x is equal to 0. So we have the matrix, instead of lambda we substitute the value 3. So we have the matrix 1, 1, 1, 1. So when cross multiplying, we have x equal to minus y. So here the eigenvector will be equal to x. X is equal to minus y. So here we'll be having minus y comma y. Let us take y to be arbitrary, negative 1. Here it's negative 1. So when y is equal to negative 1, first entry will be 1 and second entry will be negative 1. So this is our next eigenvector. Okay, now we'll normalize the eigenvectors to get P. In order to write P, we will be finding the normalized eigenvectors. For that, we have v1 is equal to, what was our v1? v1 was 1, 1, right? v1 is equal to 1, 1. So first we'll find norm of v1. So norm of v1 is nothing but root of squares of these entries. Okay, that is 1 square plus 1 square. So that is equal to root 2. So norm of v1 will be equal to root 2, and then we'll be finding new eigenvector u1, which is equal to, we'll just divide it all the entries by root 2 by the norm. Okay, 1, 1. So we will be having, this will in fact be equal to 1 by root 2, 1 by root 2. This will be our new vector u1. Okay, what we do is we'll just divide by the norm of v1 to v1, which is 1 by root 2 v1, that is our new u1. And similarly u2, for u2 also we have v2, we have v2 is equal to 1 comma negative 1. So when this 1 comma negative 1 also, we will be having norm of v2 will be equal to 1 square plus negative 1 the whole square, so which is equal to root 2. And then what we do is we'll just divide v2 by the norm of v2. So v2 was 1 comma negative 1. When dividing by root 2, we have this particular vector. Okay, now our p, in the initial case to form p, what we do is we'll just write the eigenvectors as the first column and the second column. But instead of the eigenvectors, what we do is we just write the vectors with the vectors which was divided by the norm. Okay, which is we'll write this is p, and p is formed by the first column is given by the first normalized eigenvector, which is 1 by root 2, 1 by root 2. This is u1. Okay, and we write u2 as the second column, which is 1 by root 2, and here it is negative 1 by root 2. So this will be our p. This this is the way to find p only in the case of real symmetric matrix. Okay, so we have p, and then to get d in the similar way, this u1 was the eigenvector of the eigenvalue 5, so we'll just write 5, and the all other entries are 0 for that column. And then u2 was the corresponding eigenvector of the eigenvalue 3, so we'll just write 3, and we'll make the we'll just give the entries to the diagonals, and then all other entries are 0. So we have our d also. Now we'll verify. What do we verify? We'll just see p transpose d p is equal to a. Okay, we'll just verify that. Yeah, so we need to verify that a is equal to p d p transpose. Okay, a equal to p d p transpose. P transpose comes the last. So we have, first we find what is PD. P into D, and P into D is given by 5 by root 2, 3 by root 2, 5 by root 2 into negative 3 by root 2. Now what we do is we do P D P transpose. Okay, we'll just multiply P transpose here. Here we multiply P transpose. So what happens is we'll get the matrix 4 1 1 4, which is equal to E. So this is the case of real symmetric matrix. In the case of real symmetric matrix, we need not find P inverse. Like we in the last problem, we were finding the adjoint of the matrix and cofactor and taking the transpose, and we were able to find P inverse. In this case, we need not find P inverse since we have the spectral theorem. That is the advantage of the spectral theorem. We can directly use the P transpose. Okay, so before defining P, you should remember to normalize the eigenvector. Okay, that is divide by the norm. So now we'll just go for a 3 by 3 problem. Yeah, similarly, we have the using the spectral theorem, we are asked to diagonalize this particular matrix A by finding the orthogonal matrix P and the diagonal matrix D such that A equal to P D P transpose. That's a question. Okay, so we have A. What we first do is we'll just find A is a real matrix. So we just see whether A transpose is equal to E. Okay, so here A transpose is equal to, similarly it's equal to A, so it's a real symmetric matrix. And now what we can do is we can apply the spectral theorem. So by to use the spectral theorem, we need to find the eigenvectors first. So for that, we have the eigenvalue determinant of A minus lambda I equal to 0. So we have lambda equal to 2, lambda equal to 4, and lambda equal to 2 again. Okay, and in this, every real symmetric matrices are diagonalizable. Okay, so we need not, we will get 3 independent eigenvectors. So let's see what are the eigenvectors. When lambda equal to 2, we have the matrix, this particular matrix. Okay, 0 0. While finding A minus 2y, we have this one, and instead of x, let it be x y z, then it would be easy for you to understand. So when multiplying this both matrices, first will be 0 plus 0 plus 0 equal to 0 0 0. Okay, okay, let me make it more clear. So this matrix into x y z is equal to 0 0 0. So on multiplying, we have 0 into x plus y plus z equal to 0. So in both the cases, we have the same result. So this will imply y is equal to minus z, which means we have x minus z and z. So we can arbitrarily choose two values. Let x be equal to 1 and z be equal to 0. At that time, we have 1 0 0 1 vector. let us choose an independent vector. Okay, since x was 1, let me take x to be equal to 0 and z to be equal to negative 1. So this will be 1 comma negative 1. Okay, so we have the two vectors. You can choose it arbitrarily, that's fine. And in order to get, since it is an arbitrary matrix, in order to get p, what we do is we'll just normalize them. Okay, so before normalizing we need to find v3 also. So lambda is equal to 4 was the other eigenvalue. So we'll just see what is a minus 4i into x, and we have the matrix. Let x be x, y, z. So here on solving you get what you get is, from the first equation, if this is equal to x, y, z, from the first row you get minus 2x plus 0, y plus 0, z is equal to 0. So this implies x is equal to 0. And from the second row you have 0 into x minus y plus z is equal to 0, which implies y is equal to z. So for x, y, z, your x, y, z will be equal to x is 0, and y, since it's equal to z, let it be y, y. So substituting an arbitrary value for y, let it be 1. So it will be 0, 1, 1. So this is our third eigenvector. Now what we can do is we can normalize the three vectors. So our v1 was 1, 0, 0, and taking the norm will be root of 1 square, which is still 1. So your u1 is equal to v1, which is 1, 0, 0. Okay. Now when coming to u2, our v2 was 0, 1, negative 1. So taking the norm, what will be the norm? Norm will be root of 0 square plus 1 square plus negative 1 the whole square. So that is equal to root 2. Okay, so u2, your u2 will be 1 by root 2 of v2, 1 by root 2 into v2. So you have u2, and also you can find u3 by finding the norm of v3, which is again root 2, then divide it by root 2 to get u3. Yeah. Now we'll form P by writing. How will you get P? You will be writing U1 as the first column, U2 as the second column, and U3 as the third column, and you have P. You have D. Your D will be equal to the first eigenvalue because your U1 was corresponding to 2. Your U2 was also corresponding to 2. So you write the first diagonal entry as 2, and also as the second diagonal entry you have 2. And for u3, u3 was corresponding to the eigenvalue 4. So you have the third diagonal entry as 4. You find D, and now you verify what is P, D, P transpose. Okay, so you multiply P, D, P transpose. So P into D gives you this particular matrix, and then multiplying it by P transpose, taking the transpose of P and multiplying, you will get A. So A is, hence the spectral theorem is verified. Okay. Now we will be looking at a new concept of finding using the power method to find the dominant eigenvalue. Okay, if suppose a particular matrix is having a unique dominant eigenvalue, which means if you are listing all the eigenvalues, if the biggest largest eigenvalue is a unique one, which means it is not repeated, that if that particular eigenvalue is not repeated, and if it is having a unique dominant eigenvalue, then we can use the power method to find the eigenvalues and the eigenvectors. That is a iterative method. So coming to the power method, it is an iterative numerical technique, and it is used to find the dominant eigenvalue and also its corresponding eigenvector. Now the power method converges if this dominant eigenvalue is unique. There is a condition that the dominant eigenvalues are unique. So if suppose lambda 1, lambda 2, etc., lambda n are the eigenvalues, then we must be able to let this lambda 1 be the largest eigenvalue. Then lambda 1 should be greater than all other lambda. Okay, it should be strictly greater than. It should not be repeated. That's one case for the power method to converge. And also the initial eigenvector should have a component in the direction of the dominant eigenvector. We'll see what that means by doing some problem. Okay, so now let's see some problems related to the power method. Yeah, so before that we'll be dealing with the procedure. How will we do the eigenvector problem? So for that what we need is, we'll be having a particular matrix A, and also we'll be provided with an initial vector, we'll say x0 not equal to 0. We'll be given a particular initial vector, and in the first step what we do, is we'll just find y raised to k plus 1. Okay, yk plus 1th vector. How do we find that? We'll just do axk. So we are having x0. So since we are having x0, we can find what is y1. Y1 will be equal to ax0. Okay, y2 will be equal to ax1. In a similar pattern, we'll follow the similar pattern. It will be clear when we do the problem. And if we have yk plus 1, we'll do alpha k plus 1 as the maximum of this yi. Okay, axk will be a particular column matrix, and this using this column matrix, you just find the maximum of that particular entries. And then what you do is you will just find new xk plus 1 by just dividing alpha k plus 1 with into this yk plus 1. Okay, and you will see the value of alpha k approximates the dominant eigenvalue. We'll make it clear using a problem. Okay, so now let's try this problem using the power method to find the dominant eigenvalue and the corresponding eigenvector of a given matrix, starting with the initial vector. So you are given with the initial vector x0 is equal to 1 0. So in the first step, what we do is we'll just consider the initial given vector, which is x0, which is 1 0. Now we'll be finding y1. So y1 was equal to ax0. So we have the matrix A and we have x0. We'll just multiply them. So this will be 2 into 1 plus 1 into 0, which is 2, and here you have 1. So y1 is 2 1. Okay, and now we'll find the largest, the alpha 1, which is the largest component of y1, that is 2. Okay, 2 is the, here we have 2 and 1. Among them, the largest component is 2. So we choose this 2, and what we do for this 2 is to get x1, we divide this entries with 2. Okay, the same y1 with 2. So we'll be having x1 is equal to 1 by 2 into 2 1. So when we divide with 2, we have 1, and this is 1 by 2, which is 0.5. And now so we have x1. Okay, x1 is for the next iteration, and we have the approximate eigenvalue. The first approximate eigenvalue is the largest component, which is lambda. We call them as lambda 1, or in the explanation that was alpha. That's fine since it's a variable. So let us call lambda 1 is approximately equal to the largest component 2. Okay, now we have y2. How do we find y2? It's ax1. X1, like in the last step, we got what was x1, that is 1 0.5. Okay, we'll just multiply them to get y2. It is 2.5 and 2. So what we do now, we'll choose the largest component, which is our next eigenvalue, that is 2.5. And now using this 2.5, what we do, we just divide them by dividing y2 by 2.5. We have the first entry is equal to 1, and the second entry 2 by 2.5 is equal to 0.8. Okay, so this is our new x2. We'll do that for the next iteration, and our approximate eigenvalue in this iteration is lambda 2 is approximately equal to 2.5. Okay, now using x2, we'll find y3 by getting ax2. We'll just multiply the matrix and get the value of y3, which is 2.8 and 2.6. Here the largest component, our new eigenvalue lambda 3 is approximately equal to 2.8, the largest component, and we'll just divide with the largest component and get x3 by 2.8, that's 1, and here it's 0.9286. Okay, now you can see the pattern. X1, X2, X3 all had 1 in the first place and 0.9 something in the second place, right? So it is it's approaching 1 comma 1. X1, X2, X3, it is approaching 1 comma 1. So let's see the fourth iteration also what happens there. So we find y4 by getting ax3, and we have this particular matrix, and we'll divide by 2.9286 since it's the largest component. So by dividing, we have 1 here, and here you have 0.9757. See, it's approaching, it's approaching 1. The second entry is approaching 1, and also the first entry is the constant one. Okay, so our new eigenvalue is 2.93. So where is this eigenvalue approaching? It is 2.93 here, and it was 2.9 something before. So it's approaching 3, I guess. So let's see what's the result. So we have lambda is approaching 3, and our eigenvector is approximately equal to 1 and 1. Okay. Yeah. Now coming to a 3 by 3 problem. Similarly, we'll be question is use the power method to find the dominant eigenvalue. We need to find the eigenvalue and also the corresponding eigenvector. We are given A and also we are given the initial vector x0. So x0 is given. First we'll find x1. First we'll be finding y1 and then we'll be normalizing it to get the new eigenvector and also we'll just see. So since it's x0, we'll find y1 first. By getting ax0, we'll be having a new value and then we'll find the largest component. What is the largest component? It's 4. So we'll divide all the entries by 4. So it will be 0.75, 1, 0.75. Okay, see, it was 0.75, now 1 and 0.75. Our new eigenvalue approximation is lambda 1 is equal to 4. And now in the second iteration, what happens? y2 will do ax1 and we have this particular thing, and here also the largest component is 3.5. So here we have 1 on dividing by 3.5, each entry by 3.5, we have 0.7143, 1.7143. See, it is similar to, means it's almost nearest to 0.7, right? And our new lambda 2 is 3.5. Before it was 4, now it's 3.5. Now let's see what happens in the next case. So using x2 we find y3 and we have this, and still the largest component is in the middle. So we have, by dividing by the largest component, we have 0.7083, 0.7083. See, it's approaching 0.7. And now when coming to lambda 3, it's 3.4286. I think it's going again nearer to 3.5 or 3.4. Let's see. Let's do one more iteration. You should do 4 iteration to make a conclusion. Okay. So now coming to the fourth iteration, y4 is equal to ax3 and you have this particular column vector, and now your eigenvector is about 0.7, right? In first and third entry it is 0.7 and here it is 1. So now coming to lambda 4, it's 3.4166, something like that. So we'll just take it to be 3.4. Your eigenvalue will be approximately equal to 3.4 and your eigenvector will be 0.7, 1 and 0.7. So coming to the conclusion, your dominant eigenvalue. New eigenvalue and the dominant eigenvalue is approximately equal to 3.414 and your new eigenvector is 0.707, 1.707. Okay, thank you.